Hi folks, in this video we're going to be looking at exponents and roots. So let's start with exponents. What's an exponent? An exponent is that little number you see to the upper right of another number. So for example, 2 to the third power, that's the exponent. And we call this the base. And the exponent is telling you how many times to multiply the base by itself. So this is saying multiply the base 2 3 times. 2 times 2 times 2. So exponents are really a way of showing multiplication. So 2 times 2 times 2 is 8. When people are just starting out with exponents, the temptation is to treat it as 2 times 3 and think of this as 6. But that is not correct, right? It's 2 times itself 3 times. So for example, 5 to the second power, which we call that squaring a number. 5 squared is 5 times itself 2 times. So 5 squared is 25. Now, what about negative numbers being raised to a power versus positive? Let's see how that works out. Let's look back at what we did. 2 to the third power, that's a positive number, and we know that we got a positive answer. Now, in this case, if we said, let's say 2 to the fourth power, we're going to get 2 times itself 4 times, which is 16. Now let's try it with a negative 2. So negative 2 to the third power means negative 2 times itself 3 times. Let's think about this. Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. So we actually get a negative this time. What about 2 or negative 2 to the fourth power? Well, now it's negative 2 times negative 2 times negative 2 times negative 2. And that's going to give us, we already know this part gives us negative 8. Negative 8 times negative 2 is positive 16. What's going on? Well, I'll show you the rule. The rule is when you have a positive number to an odd power, you get a positive number. When you have a positive number to an even power, you get a positive number. When you have a negative number to an odd power, you get a negative number. And a negative number to an even power, you get a positive number. So notice there's only one way to get a negative number with exponents, and that's to start with a negative number and raise it to an odd power. Every other combination gives you positive numbers. So let's write that rule down. A positive number to an even power is positive. A positive number to an odd power is positive. A negative number to an even power is still positive. And a negative number to an odd power is the only way to get negative. Okay, so the order here is a little different from the order here, but I wanted to highlight that this is the only one that gives you an odd answer. And the reason is a negative number multiplied by itself an even number of times will always come out positive. All right. Now, so far, all our exponents have been positive. What happens if we change the exponent? And let's start with 0. So I mean change the exponent from being positive to being 0. Well, I won't go into the reason for this, but any number to the 0 power is 1, which might seem a little weird at first. So for instance, 18 to the 0 is 1, and 512 to the 0 is 1. Anything to the 0 is 1. Actually, I should say any non-zero number to the 0 is 1. So 0 to the 0 is kind of tricky, and we won't worry about that. So any non-zero number to the 0 power will always give you 1. So we can write that rule as any non-zero number to the 0 power equals 1. Okay, what about raising something to the first power? That one is a little more intuitive. You're always just going to get the number itself. So any number to the first is the same number. So people usually find that a little more intuitive. 5 to the 1 is 5. 150 to the 1 is 150, and so on. Let's look at numbers that we call perfect squares. If I take an integer like 6 and I square it, I get 36. So 36 is the perfect square. Or if I took the number 20 and squared it, I'd get 400. So 400 is a perfect square. Now, so basically a perfect square is any integer squared. Another way to say that is that a perfect square has all of its prime factors raised to an even power. So if I were to prime factor 36, for example, I could say it's 4 times 9, which is 2 times 2 and 3 times 3. So notice its prime factorization is 2 squared times 3 squared. And since both of these are even, that tells me that must be a perfect square. So the prime factorization of 400 happens to be 2 squared times 5 squared. Sorry, I meant to say 2 to the 4th times 5 squared. And we notice that that's an even number and that's an even number, and that tells us that that must have been a perfect square. So a perfect square is a number other than 0 or 1. I didn't mention that before. Other than 0 or 1, whose prime factors have even exponents. And it's helpful to know the first 14 perfect squares. Let's look at what those are. We just start squaring integers. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and then I'll just list the rest. 36, 49, 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. And 15 squared is 225. So I said the first 14. Let's take it up to the first 15. It's a good idea to memorize these because they're just helpful numbers to recognize. We can also talk about perfect cubes, and that's just going to replace these numbers, the exponents, with threes, which are called, that's called cubing a number when you raise it to the third power. So a perfect cube just comes from taking any integer like 4 and cubing it, or raising it to the third power. 4 to the third is 64. 4 times 4 times 4. And then another way to say what a perfect cube is that it's a number whose prime factorizations, or the prime numbers in their prime factorization, all their exponents are divisible by 3. So 64, actually 4 is not the prime factorization of 64. 64 happens to prime factor as 2 to the 6th power, and 6 is divisible by 3. So a perfect cube is a number other than 0 or 1 whose prime factors all have exponents divisible by 3. And it's also good to memorize the first few perfect cubes. So we see one of them here is 64. So this is going to be 0 to the third, 1 to the third, 2 to the third, etc. And those numbers are 0 to the third is 0, 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, 6 to the third is 216, 7 to the third is 343, 8 to the third is 512, 9 to the third is 729, and 10 to the third is 1000. It's also a good idea to memorize the first few powers of the lower integers. Now 0 to a power is 0, and 1 to a power is always 1, so that's not anything too interesting. So we start with 2, and we want to know or memorize that, of course, 2 to the 1 is 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, and notice, of course, I'm just doubling every time. 2 to the sixth is 64, 2 to the seventh is 128, 2 to the eighth is 256, 2 to the ninth is 512, and 2 to the 10th is 1024. So it's a very good idea to be on the lookout for these numbers as powers of 2, we call them. And it's even better to memorize, for instance, you look at 32 and just say, oh, that's 2 to the 5th. Okay, also for 3, except we're not going to go up quite so high because 3 is a bigger number. 3 to the 1 is 3. 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81. And 3 to the fifth is 243. So recognize these as powers of 3 and memorize those. And we'll just do 2 more numbers. We'll do 4 to the 1, of course, is 4. 4 squared is 16. 4 cubed is 64. And we'll stop at 4 to the 4th, which is 256. Last one, 5 to the 1, 5. 5 squared is 25. 5 to the 3rd is 125. And 5 to the 4th is 625. So along with those perfect squares and perfect cubes that we did before, it's also good to memorize your powers of 2 up to the power of 10, your powers of 3 up to the power of 5, powers of 4 up to the power of 4, and powers of 5 up to the power of 4. Now we talked about raising numbers to a positive exponent and to 0. Now we can also raise numbers to a negative exponent. What does that do? Well, it might seem a little counterintuitive at first. For example, 3 to the negative 1 is 1 over 3 to the positive 1. And 3 to the negative 8 is 1 over 3 to the positive 8. So if we take this, the rule here is just any number to the negative 1 is 1 over that number. And any number to a negative number in general is 1 over that same number to the positive version. That's what we're seeing in these two examples. Now, here's the thing. Putting 1 over a number is the same as flipping the number. It's the same mathematical thing you're doing. So sometimes you're going to be putting 1 over the number. Like in this case, the number you're raising to a negative is 3. You put a 1 over it. But sometimes it's more convenient to flip the number, and that's when you have a fraction. So for example, 7/8 to the negative, let's say 2, is flipping the number to the positive 2. That's really the same rule as that, because remember, I just said putting 1 over a number is the same as flipping the number. So you can do either one, whichever is convenient. And if it's a fraction to a negative power, it's more convenient to flip the fraction and make it positive. If it's an integer to a negative number, it's more convenient to put 1 over the number to the positive power. Now let's look at what happens to a number when you raise it to an exponent in terms of getting bigger or smaller. So some number properties of exponents. Now you might think that numbers always go up, because when we think of multiplying numbers, we think of them as getting bigger. And in common examples like 3 squared, we have 3 times 3, and that is 9. So our number is going up from a 3 to a 9. But it's actually more complicated than that. It depends on what kind of numbers we're dealing with. So let's look at 10 different cases. So I'm going to make some columns where I say what kind of number the base is, what kind of number the exponent is, and then whether the number gets larger or smaller. Okay, so let's start with a base that's larger than 1, bigger than 1, and the exponent is even and positive integer. Okay, even positive integer. So one example of that would be the base is, say, 3, and we have an even positive integer like 4, and that's basically what I did last time, right? That's when I had a 2 is the same case, 3 squared. So here it'd be 3 is 3 to the 4th, which is 81. 3 times 3 times 3 times 3. So it looks like the number is getting larger, and that is always going to be the case. How about if the base is still greater than 1, but now we have an odd positive integer? So that might be like 3 to the third power. Or let's do 2 to the third power just to mix things up. Base bigger than 1, odd positive integer. 2 to the third is 2 times 2 times 2, which is 8. So again, our number is getting larger. Now let's say our base is less than negative 1, so that might be something like negative 2. And we're going to be raising the whole thing. Let's go back to the even positive integer. So for instance, 4. Well, a negative times itself an even number of times we saw before is a positive, and this is going to be positive 16. So our number is getting larger. What about, again, a number less than negative 1, but now an odd positive integer? So let's say negative 2 to the third power. Well, now we're timesing it a negative number, an odd number of times. That's going to give us a negative number, and it's going to give us negative 8. We've actually gone down. Negative 8 is smaller than negative 2, so that's going to be smaller. Let's try to neaten this up a little bit if we can, or make it a little more clear. Now let's talk about some fractions. What if we had a positive, actually let's write that as a plus sign, a positive proper fraction. So proper fraction means the top is smaller than the bottom, like 2/3. And what if we raise that to a positive even number? I mean positive even integer. So let's take 2/3. Let's take a simpler one. Let's take 1/3 and let's raise it to a positive even integer like 2. Well, 1/3 squared is actually 1/9. So when you square 1/3, the number goes down. It gets smaller. So you're starting to see that numbers don't always get bigger when you apply exponents to them. Okay, let's do a negative proper fraction. To an even positive integer. So what if we had negative 1/3 and we squared it? Now we're going to get a positive 1/9, and our number has gone up because any positive number is bigger than any negative number. So our number got larger. Now let's revisit that positive proper fraction, but let's make it an odd positive integer. And let's see what happens. We want a positive proper fraction, so we could go with 1/3, and we could do an odd positive integer like 3, and that's going to give us 1/27. So the number's going down, smaller. Just like up here, it's really the same thing. Even or odd doesn't make any difference there. And now you probably guessed we're going to look at a negative proper fraction with an odd positive integer. So a negative proper fraction, let's do negative 1/2. And we want an odd positive integer. So that's going to be something like 3. And that's going to give us negative 1/8. So what happened there? We went from a negative 1/2 to a negative 1/8. Negative 1/8 is actually less negative than negative 1/2, so it's actually bigger. So the number went up, it got larger. Okay, we're going to do 2 more cases, and we're going to jump to fractional exponents now. We're going to look at a base that's greater than 1, and we're going to look at a positive proper fraction. So positive proper fraction now in the exponents. So for example, we could have a 9 to the 1/2. 9 to the 1/2 is 3. We're going to look at that at some point. We're going to talk about how those fractional exponents work. Just to give you a preview, that means the square root of 9. So the number is going down, smaller. And finally, let's look at a positive proper fraction here in the base and a positive proper fraction here in the exponent. So for example, you could have 1/25 to the 1/2, and that is 1/5, again, because that means the square root of 1/25. Let's not worry about y right now. Just know that that is going to take my number and actually make it larger. Now let's talk about something we call radicals. Radicals, you may commonly see them as square roots. They look like this. And the most common one is we call a square root, which is, there's sort of an invisible 2 there. When you take roots of two numbers and you add them up, so we're going to talk about adding and subtracting radicals. When you have the square root of two numbers added, it is not equal to the square root of one plus the square root of the other one. That's not how radicals work. So for example, if I had the square root of 4 plus 36, that does not equal the square root of 4 plus the square root of 36. That would be 2 plus 6, which is 8. But what the square root of 4 plus 36 is really equal to is the square root of 40. And if we did that on our calculator, we would find that it's equal to about 6.32. The decimal goes on forever. I just rounded that. That's what the squiggly equal sign means. It means about equal to. So clearly 6.32 is not 8. So don't try to add things separately when they're under a radical or a root. You've got to add them first, and then you can take the square root. What about multiplying radicals? What happens if I take any root, so the m could be a 2 or 3 or anything, some root of a times the same root of b, so this is only applying when these roots match up. Now you can multiply them underneath. You can go like this. That's the m root of a times b. So likewise, of course, you can go the other direction. If you had the m root of two things being multiplied, you can root them separately. Okay, so for example, the square root of 4 times the square root of 25 is the square root of 4 times 25, which is the square root of 100, which is 10. And then you could also see that because the square root of 4 is 2, and the square root of 25 is 5, and 2 times 5 is 10. So that's perfectly allowable. So I said it works the other way too. I'm just writing that in reverse. So for example, I could have the square root of 400, and I could decide to break that into the square root of 4 times the square root of 100, and then that would be 2 times 10, or 20. What about dividing radicals? They also can be combined, just like when you multiply. So what I mean by that is if I have the m root of a over the same root of another number, I can just divide the a and the b and have them all under one radical. Or going back the other way, I can say if I have two things on top of each other, I can treat that as two separate radicals. So for example, if I had the square root of 20 over the square root of 5, I can call that the square root of 20 over 5. And 20 over 5 is 4, and the square root of 4 is 2. So that makes sense to think about it that way. Or if I had down here, let's say I had for example, the square root of 36 over 25, I can treat that as the square root of 36 over the square root of 25 separately, which is 6 over 5. And that's because a square root is asking us, what number do I have to multiply by itself to get that number? What number do I have to multiply by itself to get a 4? I have to get it's a 2. What number do I have to multiply by itself to get 36? The answer is 6. And for 25, I have to multiply 5 by itself. Now, of course, not all numbers are what we call perfect squares. So these are all perfect squares. 4 is a perfect square because its square root is an integer. 36 is a perfect square. Its root is an integer, and same with 25. But most random numbers you pick are not going to be perfect squares. For example, the square root of 7 is some number, some decimal that goes on forever. It's 2 point something. So, but there are a few that it's good to memorize approximately what they're equal to. And those are the square root of 2, which is about 1.4, the square root of 3, which is about 1.7, and the square root of 5, which is about 2.2. So those are good to memorize. All right, now let's talk about some square roots and cube roots of some decimals and numbers with zeros after them, larger numbers. What do I mean by that? Well, for example, let's look at square roots of small perfect squares. For example, 0.0009 is a perfect square, and that's going to be equal to, well, let's say that means its square root will be a non-repeating decimal. Now, the square root of that is the square root of 9 over 10,000, and that's the square root of 9 over the square root of 10,000, and that is 3 over 100, which is 0.03. So the square root of 0.009 is 0.03, and what I want you to notice is that there is an even number of decimal places, 1, 2, 3, 4, and that the answer, the root of it, will have exactly half that number of decimal places, which is 1, 2. So 2 is exactly half of 4. Now we could also look at square roots of large perfect squares and notice a similar pattern. For example, let's take a look at 400. The square root of 400 is 20. And the thing to notice here is that if you have a large perfect square, the number with trailing zeros, you have to have an even number of zeros, in this case 2, and the root of that, the square root, is going to have half that number of zeros, in this case 1 0. Now let's talk about a similar thing but with cube roots. The cube roots of small perfect cubes. So for example, 0.000008, that's a perfect cube. It's going to have 1/3 the number of decimal places. The cube root is. So this has 1, 2, 3, 4, 5, 6 decimal places. We're going to expect 1/3 of that, or 2 decimal places, in the cube root. And indeed, the cube root of 0.000008 is 0.02, 2 decimal places. Now, if we look at the cube root of large perfect cubes, we're going to notice a similar pattern to what we've been talking about. Let's look at 1,000. So if there's trailing zeros in a large perfect cube, then the number of zeros is also going to be 1/3 the number of zeros in the original. So here we have 3 zeros. So we're expecting 1 0 in our cube root of 1,000. So the cube root of 1,000 equals 10. 1 0. So those are good patterns to keep in mind. And that's going to bring us to the end of the video. So that was exponents and roots, and I hope that was helpful. We'll see you next time.